Hello, this is the video for section 4.4, intermediate forms and L'Hopital's rule. Okay, we're coming back to limits again, and you thought from chapter 2 or not, but here it comes. Now, these are our learning objectives. We'll be able to identify the indeterminate forms of functions and then use the L'Hopital's rule to apply. It doesn't mean that we should apply it blindly. And we'll look at one example where you don't need to use the L'Hopital's rule at all. But you use it only when appropriate. Okay. Now there are about four indeterminate forms. Right. If you have 0 over 0 or infinity over infinity. In fact, this is the hypothesis of what the L'Hopital's rule. Okay, this is the core of that. Now, if you have 0 over 0, what do you say? Is it 0? If you consider the numerator not to be 0, another number, if you have 0 over 4, we know that is what? This is 0. But you have 0 over 0, it's indeterminate, or infinity over infinity. In the first place, infinity is not a number you really know. If you think it's 1,000, it is maybe 10,000, maybe trillion, okay, or quadrillion, or whatever, okay? So the L'Hopital's rule says that if you have two functions, f and g, that are differentiable, and then the g, the derivative of the d is not 0, okay? Because we're going to find a quotient of that. Now, if the limits of f exist, the limit of g also exists, and both what 0, and or the limit of what f is either positive or negative infinity for both of them, then we can have this type, which could be what? If you have the limit of f divided by g as what? It's 0 over 0, then we have this kind of form. Or if it is positive infinity over infinity, then you have what? You have this one. Okay. So if you have this order, it says that differentiate the numerator and differentiate the denominator separately. You do not use the quotient rule. Just differentiate the top and differentiate the word denominator. Okay, and then take the limits. All right. So let's here is some of the notes that three notes I want you to pay attention to. The L'Hopital's rule says that the limit of a quotient function is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. That is, when you have 0 over 0 or what? Infinity over what? Infinity, provided this is what satisfied. Okay. So note also that we can apply this L'Hopital's rule more than one time. Okay. I'm going to use h anytime I'm applying. I'm going to use h. So if I see that equal to something, I put h, means I'm applying the L'Hopital's rule. The second is that the limit, what we just talked about here, okay, it also holds for what? The one-sided limits. Okay. So if you have a, I can approach plus what? A from the positive, a from the negative, as well as this one. Okay. Then the third one is that, okay, for a special case when f of a is equal to g of a and that is equal to 0, then of course f prime and g prime are both what? Continuous, and g prime at a is not 0. Okay. That's a constant function, basically. It is easy to see why the L'Hopital's rule is true. In fact, using the alternative form of the definition of a derivative, we have this. Okay, so you have a limit a goes to x goes to a, and the derivative of the top and the denominator is equal to this. Okay, in this case, if from chapter 2, the limit of what? F prime of a is the same as what? The limit of what? F of x minus f of a divided by what? A minus what? X minus a. And the same applies to the g of g, what do you call it? G prime of x, which is what? Which is also given by this. Now, if you simplify this is just going to be this, the denominators will cancel out. Okay, this will cancel out. And then you have the top over what? Over the bottom. Okay, so when you do that, you're going to have this approach, and which is basically, of course, the f prime, okay, f of a is equal to g of a, and this is what? This is 0. So this is just going to be what? This is going to be that. So if you are finding the limit of this is saying that it's a simple case. You have the limit x goes to a of f of x, so f of x divided by the g of x is equal to the limit x goes to what a of what f prime of a of x over what g prime of what. This is what we just proved. Now it is more difficult to prove the general one because this is just for a specific case where this is true. All right, so take note of that. Now let us apply this to some equations. Now let's see, as s goes to what, find the limit s goes to 1 natural log of x divided by x minus 1. Now as s goes to 1, you have what, natural log of 1 over what, 1 minus 1, and that gives me 0 over what, 0. So that means I can apply the L'Hopital's rule. Okay, I put h there. So that means that if you differentiate, okay, here your f of x is the natural log of what, x, and then your g of x is what, x minus 1. Minus 1. So if we differentiate, this goes to what, 1. What's the derivative of that? This is 1 over our x, right, divided by 1. And that gives me the limit x goes to 1 of what, 1 over x. And then this case is in the, you can direct substitution, which will be 1 over 1. And so the answer is what? The answer is 1. Therefore, what we have there, the limit s goes to 1 of what, natural log of x over x minus 1 is equal to. Okay, let's consider other examples. Using the limits where appropriate. Okay, now let us see, when x goes to infinity, what do we have? We always check the hypothesis of it. E to the x is what? It goes to infinity. And then if x goes to infinity, you have infinity squared. It's going to be a big value. So you have infinity over infinity. Okay, the first one we had 0 over 0. This is infinity over infinity. So we can apply the L'Hopital's rule. And so let's apply it here. We put h there, indicating that we're applying the L'Hopital's rule, meaning differentiate the numerator. So this is equal to what? The limit x gets bigger and bigger. So differentiate the numerator, you have e to the x, and differentiate what? The denominator, which is what? 2x. So again, when you plug in the e, x goes to infinity, you get what? Infinity over what? Infinity. So that means that we have to apply the L'Hopital the second time. Okay. Remember, I told you can apply it more than once. So let's differentiate. This will give me the limits. X goes to what? Infinity. Differentiate the top, you have what? E to the x. Differentiate the denominator, you have what? 2. So this gives me what? E to what? To infinity over what? 2, which is what? Which is a very big value. So the answer is what? Positive what? Infinity. Positive infinity over 2, which is what? Okay. Now, this particular one, yeah, a pi goes to what? Pi from the what? Negative from the left. Okay, I don't need to apply the L'Hopital's rule here. Okay, because let's substitute the pi into this. This will give me sine pi from the what? From the right. Okay, and then 1 minus cosine of what? Pi from what? So basically, what the sine of pi is what? Is 0. And then we have what? 1 minus 1, because cosine of pi is actually what? It's negative 1. So this gives me 0 over what? Over what? Over 2, which is what? 0. So you can see that when if I substitute this and the had was 0 over 0, that is when I will apply the L'Hopital's rule. So here, the L'Hopital's rule is not needed. Okay, not needed in this case. Okay, so that is one type. We have what? Talk about 0 to over 0 or what? Infinity over what? Infinity. One situation where you don't need to apply the L'Hopital's rule. So it is important to always check the hypothesis of the what? Of the L'Hopital's rule. That is, check this before you apply. Now, the second form is a product. We call it what indeterminate what products. You can, if you have 0 times infinity, if you consider the 0, then it turns to 0. If you consider it, so we cannot determine this particular case. So this is an indeterminate form. All right. Now, what do we do and how do we use the L'Hopital rule? Okay. Now, what we do is this. Okay? If the limit x goes toward a is 0 and g goes toward that is what? It's infinity, or it could be negative infinity. That is when we have that type. Okay. Now, there's a struggle between what? The f and g. If f wins, the answer is what? 0. If g wins, the answer is what? Positive infinity or negative infinity. So what we do is that, or there may be a compromise where the answer is finite non-zero number. This kind of limit is called what? The indeterminate form type of what? That's an indeterminate what? Products. Now, how do we handle this? We write it as a quotient. We write the product as a what? As a quotient. So if I have f times g, I can express it as what? F divided by 1 over g. Or if I have the same thing, I can have g over 1 over f. So the question is that when do we use this form? And when do we what? I'll show you examples in which in certain situations this works best. In the other situation, this is how it should be. Okay. Now, let's look at this example. You have what? The limit s times what? Natural log of what? X. Okay, it's a product. Now, if s goes to 0, right? Let's see what happens. The solution, you have what? The limit x goes towards 0 from the right of x times natural log of what? X. Now, what is this? This is what? This is 0. Natural log of what? 0 is actually what? Undefined. Okay. Natural log of, you have what? 0 times what? Undefined. So we use infinity for that. Now, when you have this kind of function, now this is like f times g. Is it going to be what? F divided by 1 over what? 1 over g, or will we use g over 1 over what? Okay. Now, if you write this as 1, if you use this part, this approach here. Okay. Now, if you use this approach, okay, let's see how that is going to be. Natural log of x goes to what? 0. Yes. My g is what? Natural log of x. So keep that. Natural log of what? X over 1 over what? 1 over x. Okay. Now, if you differentiate this, right? Let's check for if it goes to 0. The denominator will be what? This is what? Infinity. That is going to be what? Also infinity, right? Because you're going to have 1 over what? 0, which is also what? Which is infinity. Okay. That is a L'Hopital's rule type. Now, let us apply the L'Hopital rule here. We have what? The limit x goes to 0 from the right. The natural log of x over, okay, differentiate natural log of x, you have 1 over all x. And if you differentiate this part, which is the same as, okay, we differentiate that, you have what? Minus what? X raised to minus what? Minus 2. Okay. So how do you simplify that? Okay. How do you simplify that? Now, this is the same as this is 1 over our x divided by negative 1 over our x squared. Okay, so let's simplify this. So this is equal to the limit s goes to what? 0, and then we have 1 over x times negative 4 x squared over 1. Okay, which will just give me 4x. So basically what we have there is a limit s goes towards 0 from the right of what? Negative x. And if s goes to 0, this goes towards 0. So therefore, the answer, the limit, s goes to 0 from the right of x times natural log of x is equal to 0. Now, if I had used this one, it's going to complicate issues because you're going to have something like, okay, this limit here will be equal to the limit x goes to 0 of that, and then you keep the x, and then you have natural log of x all raised to what? -1. Now think of differentiating this. What's the derivative of that? Okay, if you differentiate, well, you're going to have -1, and then you have what? Natural log of x raised to a -2 times natural log, derivative of natural log, which is 1 over x. That alone. And that gets complex, complicated, becomes more complex. And so for whenever you have x times a natural log, bring whatever info, keep the natural log in the numerator, and bring the whatever there to the word, to the bottom. Right? So you're going to write it as well, g over what. Okay? Now, here, when you have a function in terms of what? In terms of e to the x. Okay, e to the x. Okay, that one, we use the other approach. Remember, we have f of g is either what? F over 1 over g. It's what? G over what? 1 over what? Okay, this is the one we just did for whenever you have what? A natural log times a certain function. We use this one. Now, whenever you have a natural log times e to the x times a function, say x or x squared, we use what? This part. Okay, so we're going to write this as the limit x goes toward -infinity of x squared, okay, times e to the what? G to the x. -infinity, this is what? This would be -infinity times. Then e to the -infinity is going to be what? 0. So this is the form 0 times what? So who wins? All right. So that is an indeterminate type. That's this type that we're going to deal with. So we're going to write it as using what? This part, f over 1 over g. And so we're going to write this as what? The limit x goes to -infinity of, x squared over e to the what? -x. Okay. X over x times what? E to the x. All right, so now let's apply the limits and see what we get. Okay. We apply the limits there. E to the, this goes to what? It goes to +infinity. Okay. Now e to the x, and this goes to -infinity. That goes to what? That goes to what? Positive for infinity. And so because the graph of that is like this. And so if you are going -infinity, that can be done there. So then we can apply the L'Hopital's rule here to the h. So the limit is going to be the limit x goes toward -infinity. Differentiate the top, we have what? 2x. And differentiate the denominator, you have what? E to the what? -x. So then, what do we do next? If you apply this, you have what? You're going to have infinity over, okay, this gives me, we get what? E goes to what? -infinity is positive, so that goes to positive infinity, that's a negative. So basically you get infinity over infinity. Then we what? We'll apply it again. We apply it a second time. So we apply the L'Hopital's rule again. We have what? The limits x goes to -infinity of, if you differentiate the numerator, you get 2 over what? That to be positive for e to the that. Okay. So then what is this? If e goes to what? Infinity, x goes to -infinity. This is going to be what? 2 divided by, okay. Now e goes to -infinity, that will be positive. So that is tend it to go that way in the graph. So this will be what? Positive infinity. Now, so 2 divided by a very big value will be what? Will be 0. Okay. Therefore, the limit x goes to what? Negative infinity of x squared e to the x is equal to what? Is equal to 0. So remember, whenever you have anything times or e to the x, okay, bring this to the bottom, bring the e to the x, and keep the other function in the top. In the, if you write it as a quotient. All right. Now, the c part is what? The difference. You have minus infinity minus infinity. Will the answer be 0? Okay. So this is also an indeterminate form. We call it indeterminate what? Difference. Now, how do we handle such cases? All right. Okay. Now, what we do is this. If I have the limit x goes to a is in positive infinity and that's positive infinity, then the difference will be infinity. So that gives you that type of indeterminate form. Now, what we do is that we convert the difference into a quotient. Okay, how do we do that? We use it by sometimes we find a common denominator, or we rationalize, or sometimes we factor a common factor. We factor a, and then we test the hypothesis of the L'Hopital's rule, and then apply it. Okay, so let's take an example. Exercise number 6, compute this. Now, if x goes to what? 1, guess what do I get? I get what? 1 over 1 minus 1, the minus 1 over natural log of 4, natural log of 1. Now, 1 over, you get what? This will give me 1 over 0 minus 1 over 0, which is what? Infinity minus infinity. So we're going to what? Simplify this expression. We're going to simplify this expression. Okay? So we're going to find a common denominator and then approach it to see if we can apply the L'Hopital's rule. So find what? Simplify. You simplify that. So we have what? The limit. I'm going to divide the limit. X goes toward 1. If I simplify, the denominator will be what? Will be x minus 1 times what? Natural log of x. And then the numerator here will be x times natural log of x minus 1 times what? That, which is x minus 1. Okay. So I have, this will be my expression right there. All right. Now, let's just what? Take s goes to 1 and see what we get. If s goes to 1, we have what? Natural log of what? 1 to 1. And then have minus what? 1 minus 1. And I have what? 1 minus 1, which is what? 0. Okay, so you have 0 times what? Natural log of 1. That gives me natural log of 1, you get 0 over what? 0. Because natural log of 1 is 0, and 1 minus 1 is 0. So 0 minus 0 is 0. So therefore, I can apply the what? The L'Hopital's rule on this. Okay, differentiate the top. Okay, if we differentiate the top, x goes to 1. Differentiate x minus 1. That's a product rule. So if I differentiate that part, I have what? I have x times 1 over x plus, and then keep the natural log of x, then multiply by 1. And then I have minus x. If you differentiate that, you get what? You get 1. And if you differentiate the negative 1, you get 0. Okay, so this gives me minus that. And then divided by, let's use the product rule again. You keep x minus 1 and differentiate natural log of x, you have what? 1 over x. Then plus, you keep the natural log of x and differentiate x minus 1, which is what? Which is 1. Okay, so then this will cancel that. Okay, let me write it here. Now the limits x goes to 1. The numerator will just be what? 1 plus natural log of x, okay, minus 1 divided by what we have there will be x, we get x minus 1 all divided by x, then plus what? Natural log of what? Natural log of x. Okay. So then the numerator basically becomes what? The limits x goes to 1 is natural log of x, because 1 will cancel out, and then divided by x minus 1 over x, then plus natural log of what? Natural log of x. So then let us substitute the what? The 1 into that and see what we get. Okay. So when we do that, we have natural log of 1 over, this will be 0 over 1 as natural log of 1, which is what? 0 over what? 0. And so we apply the L'Hopital rule the second time. And when we do that, we have, we differentiate this guy here. Okay. We differentiate it. We're going to write this as, let me write this, the limits. Okay. Write the limit x goes to what? 1. Natural log of x divided by, this is 1 over x plus natural log of x. And so if we apply the L'Hopital rule here, this will give me the limits x goes to 1, that is 1 over x, okay, 1 over x, and this will be 0, to differentiate minus 1 over, that will give me positive, okay, that will give me plus 1 over what? X squared, and then plus what? 1 over what? 1 over x. Okay, so when we substitute 1 into that, we have what? 1 over 1. Okay, and then 1 over 1 squared plus 1 over what? That gives me 1 over what? 1 plus 1, which will give us what? 1 half. So therefore, the limits s goes to 1, the original, there, which is what? X over x minus 1 minus 1 over natural log of x is equal to what? That's my answer. Okay, so when you have this, you got to simplify. Sometimes you have to factor some things out. We'll do more examples in class, but for now, we'll keep it like this. Okay, all right. Then the last part, type of called the intermediate word powers, and this has 3 cases in it. Okay, now these ones we have, for this type we have 0 raised to 0, infinity raised to 0, and 1 to what? Infinity. These are all intermediate word forms when you have powers of functions. Remember something I have for x raised to x, something like that, where we have to, if we're to differentiate, remember we'll use the logarithmic word. We take natural log of both sides and then differentiate from there using the log or the differentiation. Now this is finding the limit. Okay. Now whenever you have this, you have to use the natural log and then able to take natural log and then simplify before you apply the L'Hopital rule. All right. Now, all that you do is that each of these 3 cases can be treated either by taking the natural log of this function. That's your, let y equal to that and take natural log and write it as what? G of x times that, and we can explode that. Okay. And then we can, this y is the same as this. In other words, we are using this rule, y is equal to e raised to natural log of x, natural log of y. Okay, whenever you have this, this is equal to y. All right, so it's a very important rule. Now, once you have as a product, then we can treat it like we did before. Okay, so in each case, make good use of what? This rule that I've just stated here, which are this rule. All right, so we're going to take example of each of the types there. All right, first, we'll look at 0 raised to 0. Okay, so first, what do we do? Okay, let your y equal to x raised to the square root of 4x. All right, and then we take natural log of that. So we're going to take natural log of this. So that is natural log of what? Y. which is going to be square root of 4x times natural log of x. Now remember, when we use it, it's a product. Okay. Now remember, we are looking for the limit. Okay. From the limit, x goes towards 0 from the right of y. So in this case, the natural log of y, which is what the limit x goes to 0 of that of square root of x natural log of x, and this will give me what 0 times what infinity. So it becomes a product type. Okay. Now remember when we said if you have f of g, when you have this, what do? You keep, if you're involving natural log, keep the natural log in the top and divide by 1 over. So you use this word, this approach. Okay. So we're going to say, well, when I have that, then I'm going to write this as what? This is equal to the limit. X goes toward post 0 from the right of natural log of x divided by 1 over the square root of 4x. Now, which is the same as the limit x goes to 0 from the right of natural log of x, okay, divided by x raised to minus 1 half. So now if x goes to 0, okay, then if this goes to 0, you have 1 over a square root of 0, which is what? Infinity. X natural log of 0, this is what? This is infinity over infinity. So we can use the what? We can apply the L'Hopital's rule. So then we're going to differentiate this. We have the limits. X goes towards 0 from the right. Differentiate natural log, get 1 over x. Differentiate, that you have what? Minus 1 half. X raised to 1 half minus 1, which is minus what? 3 halves. Okay, now let's simplify this guy here. This is the same as the limit. Let's write it up here. The limit x goes to 0 from the right. We have 1 over x. What we have there is the same as minus 1 over, okay, minus 1 over 2 x raised to what? 3 half. That becomes the limit. X goes to 0 of what? 1 over x times 2x raised to 3 half. Now, if you simplify this over 1, you simplify that, you have the limits. X goes to 0 from the right, and that will give you 2x raised to what? 1 half. Because the 1 here will go and subtract from the 1. So now, if x goes to 0, guess what? We have what? 2 times square root of 0 is what? Is 0. Okay. So now, how do we find our original function? All right. This is where the trick comes here. So now, what we do is that the natural log, okay, x goes towards 0 from the right of your y, okay, which is the original here, it is equal to the limit x goes to 0 of what? E to what? Natural log of y. This is what we are doing. The natural log of y is what we have found this to be. So here is what? X goes towards 0 from the right. Natural log of y is equal to 0. Now, whenever you have this is the same as e raised to the limit. X goes to 0 from the right of what? The natural log of what? Y. Which we have found this to be what? To be what? 0. Therefore, this is equal to what? E raised to 0 is equal to. Okay. What we're saying is that our answer, the limit, x goes to 0 from the right of the original, x raised to square root of x is equal to what? And that gives us the answer. That is the first time. Okay. We have what? 0 raised to what? 0. Okay. Because we have 0 raised to 0. And take the limit. X goes to 0 from the right. Okay. Now, here's another example. That's infinity to what? To 0. Now, if x goes to infinity, guess what? I have what? I'm going to have what? Infinity raised to 1 over infinity. Infinity is a large value. The 1 over there would be very small, approaching 0. So this is basically infinity to what? To 0. So this is this type. Okay. So we handle the same way. We let what? Y equal to that expression on x raised to 1 over x. Okay. So then we take natural log on both sides. Natural log of y is equal to 1 over x natural log of x. Okay. Yeah, 1 over x natural log of what? Natural log of x. All right. Well, what we have there is nothing but what? Natural log of x over what? Over x. Okay. So then, if I take the limits, x goes towards infinity, okay, of my y, natural log of y, which is going to be the limit. X goes toward infinity of what? Natural log of x over what? X. Now, natural log of x, if infinity, this will be what? Infinity over infinity. So that is a L'Hopital's rule there. So let us apply the L'Hopital rule there, which will give us what? Will be the limits x goes toward infinity of 1 over x divided by 1. And then this will just be what? The natural log of, so the limit x goes to infinity of 1 over what? 1 over x. And that is what? That is 0. So like we did before, originally we are finding what the limit of my y, x goes to infinity of y, and then y is the same as what? Remember, y is the same as e raised to a natural log of y. So this is the same as the limit x goes to infinity of e raised to natural log of y, which is the same as e, then the limit x goes to infinity of the natural log of what? Y. And then we find that here, that is equal to 0. So this is equal to e, the whole of the top there is what? Is 0. So this is equal to what? This is equal to. Therefore, limit our original x goes to infinity of what? X raised to 1 over x is equal to what? We found that. Okay, so that's exercise number 63. That's a type. Then the last one, last example is, okay, have 1 raised to infinity. Okay, now if x goes to 0, guess what we have? We have what? The 1 minus 0 raised to 1 over 0, which is what? 1 raised to infinity. Okay, because the x gets smaller and smaller, it's just, that's a very big value. So that's this type. All right, we do the same thing. We let what? X, sorry, let what? Let y equal to that, this expression. 1 minus 2x raised to what? 1 over x. Then take natural log, which will be 1 over x times 1 minus what? 2x. Okay, which is the same as what? 1 minus 2x over what? Over x. Okay, that's the same thing. All right. So then we are finding the limit. We want to see the limit s goes to 0 of this, the natural log of y, which is the limit s goes to 0 of what? 1 over 2x over what? Over, sorry, this is supposed to be natural log. Oh, it's natural log. All right. So then if it goes to 0, you're going to have natural log of 1 over what? Over 0, which is what? 0 over 0. Therefore, we apply the L'Hopital's rule. Okay. So to the h there, differentiate. So the limits x goes to 0 of natural log of 1 minus 2x over x. Okay, so when we apply this, okay, you apply the h now. we have for the limit x goes to 0. Differentiate that, you have 1 over what? 1 minus 2x times the derivative of that, which is minus 2. Then everything divided by the derivative of x is what? Is 1. So this is equal to the limit x goes to 0 of, we have for minus 2 over 1 minus what? 2x. Now, if x goes to 0, you have for minus 2 over 1 minus 0, which is what? Negative 2. So if that is negative 2, then let's go back to our original. The limit x goes towards 0 of the original, which is 1 minus, okay, the y. Because we said let y equal to that, is equal to e raised to, so the limit x goes to 0 of e raised to a natural log of what? Y. What will give us then? E raised to the limit x goes to 0 of what? Natural log of y, which we found this to be what? We found this to be e raised to what? Now, e raised to negative 2 is what? 1 over our e to. Therefore, your final answer is this, that the limit x goes to a 0 of 1 minus 2x raised to 1 over x is equal to 1 over what? 2. Okay. So that brings us to the end of this section, and then I'll see you